Hello, my name is Irvan Jahja. This is a joint work with Haifeng. We are both from the National University of Singapore. In this work, we propose a novel framework for designing sublinear algorithms in T-interval dynamic networks. Dynamic networks are computer networks whose topology can change over time. A particularly widely used model for dynamic networks is the so-called T-interval dynamic networks model. This T-interval dynamic network model has been extensively used in the literature. In a T-interval dynamic network, there is a fixed set of n nodes that proceed in lockstep rounds. Each node has a unique ID. The set of edges in the network can change arbitrarily or adversarially from round to round, but the only promise is that for every T consecutive rounds, the topologies in those rounds must contain a common spanning graph. The following gives an example T-interval dynamic network with total 4 rounds, where each round has its own topology. One can easily verify that round 1 through round 3 has a common spanning subgraph, and similarly, round 2 to round 4 also have a common spanning subgraph. Hence, this is a T-interval dynamic network for T equals 3. Within the context of T-interval dynamic networks, we are interested in the following fundamental problems in distributed computing. First, the count problem aims to compute the exact total number of nodes in the dynamic network. Next, the max problem aims to determine the maximum input value among all the nodes, assuming each node holds some input value. Similarly, the sum problem aims to compute the sum of all the input values held by all the nodes. Finally, the leader election problem aims to select a unique leader, while the consensus problem aims to achieve consensus among all the nodes. We define time complexity to be the number of rounds needed for the algorithm to output and terminate under the worst case input and worst case dynamic network. We will use the standard broadcast conjugate model for communication. Namely, in each round, a node can send a single message of O log n size to all its neighbors in that round. All messages will then be received by the end of the round. A node does not know its neighbors beforehand or before it receives messages from them. Also, a node does not know the topology in each round. In T-interval dynamic networks, all these problems are non-trivial to solve. This remains true even when T is infinity. The central difficulty here is that the topology changes can be adversarial, and the algorithm cannot predict all the following: how the topology will change, which edges will be removed, which edges will be created, and so on. In the case of T equal infinity, even though there is a stable backbone topology that remains there in all rounds, the algorithm does not know which edges belong to the stable backbone. Existing algorithms usually overcomes this difficulty by directly collecting all inputs or all IDs from all nodes to one place in the network. More specifically, these algorithms usually solve these problems as a byproduct of solving token dissemination. In the token dissemination problem, each node starts with a token, and the goal is for each node to collect all n tokens. Obviously, if we solve token dissemination, then we can solve count, max, sum, leader election, or consensus. On the other hand, token dissemination incurs at least omega n time complexity. This is because a node needs to collect n tokens, and so if the node has a constant degree, then it must take omega n rounds to do so. In turn, all these algorithms take omega n time complexity to solve count, max, sum, and so on. There are also a few algorithms in the literature for solving count without using token dissemination, but they also incur at least omega n time complexity. Even though all existing algorithms for solving these problems take omega n time complexity, one would naturally conjecture that omega n is not a hard lower bound for any of these problems. After all, this different from token dissemination, these problems do not fundamentally require collecting ON information. For example, in the count problem, we simply need to know the total number of nodes. We are not trying to learn all their IDs. Because of this, it seems quite obvious that using token dissemination to solve count is likely an overkill. In fact, for all these problems, there is only a trivial lower bound of omega d, where d is the diameter of the network. Since the network here is dynamic, we will not be looking at the diameter of the topologies in each individual round. Rather, we will use the notion of backbone diameter. Intuitively, it is the diameter of the stable spanning subgraph of the dynamic network. The omega d lower bound holds, since all these problems need information from across the entire network. Now, if d is theta n, then obviously there is no hope of solving this problem in small o n time. But when d is small, it seems that we should be able to solve these problems in less than n rounds. But despite such natural thoughts, however, no existing algorithm can achieve this. In particular, we note that all the existing algorithms continue to require omega n time complexity, even when d is as small as a constant. Putting it another way, these algorithms still incur at least linear time complexity, even when d is O1. As the central contribution of our work, we proposed a novel framework for designing algorithms in T-interval dynamic networks when t is not too small. Our framework builds upon a complementary set of techniques. By applying our framework to the count problem, we are eventually able to design a novel deterministic count algorithm with only d cubed log square n time complexity. Our algorithm is thus the very first count algorithm under our settings that does not have a theta n term in its time complexity. Note that prior to our work, all count algorithms have omega n time complexity, and this omega n time complexity remains first, even if t is infinity, second, even when d is a constant, third, even if we allow randomization, and fourth, even if we are trying to solve approximate count instead of exact count. Furthermore, the time complexity of our novel count algorithm becomes sublinear when d is O n to the power of a for some constant a smaller than 1/3, and is exponentially faster than all existing count algorithms when d is polylogarithmic. Our novel algorithm framework can also be applied to solve maximum, sum, leader election, and consensus. By doing so, we eventually able to obtain a novel deterministic algorithms for solving all these problems as well, with the same kind of complexity as our count algorithm. Again, our algorithms are the very first algorithms for solving these problems under our settings that do not have a theta n term inside this time complexity. Our paper further describes how our framework can be used to solve other problems. Our results have several interesting implications. First, our results confirms that count, maximum, sum, leader election, and consensus are all indeed easier than token dissemination. This implies that future research can benefit from approaching these problems directly rather than indirectly via token dissemination. Second, a series of prior works have established omega poly and lower bound for solving count, even when the diameter is just a constant, in a number of models that are related to the T-interval model. Our d cubed log square and upper bound for count essentially tells us that such a lower bound can never carry over to the T-interval dynamic networks model. In the remainder of the talk, I will present more details about our novel framework, as well as about the techniques involved. Specifically, I will explain how to solve the count problem by using our framework. To solve count, let's first assume that there is some distinguished root node in the network. Our algorithm does not actually need this assumption, and you can take a look at our paper to see how this assumption can be avoided. As a starting point, if the network is static and its topology never change, then count can be efficiently solved in OD rounds. This can be done by doing aggregation over a tree. Namely, first we've built a distributed spanning tree rooted at the root node. Here, the red edges are those edges chosen to be included in the spanning tree. Next, each node contributes a value of 1. These values are then propagated upstream along the tree, while being aggregated at intermediate tree nodes. Finally, the root node gets the sum of all the values, which is the exact count of the nodes. In a dynamic network, however, the changing topology can disrupt the spanning tree. Namely, a tree edge may no longer exist when we try to use it, causing the value from some nodes to get stuck somewhere in the middle of the tree. It is important to note that by the T-interval model, even if after this topology changes, there must still exist some path of length at most t from every node to the root. For example, here, the node with the value of 2 still have a path to the root. But the problem is that this path is not contained in the spanning tree, and this is why the value gets stuck. So the problem here is actually somewhat fundamental. Because the topology changes can be adversarial, the algorithm cannot predict which path will survive. Putting it another way, whichever path we decide to include in the spanning tree, the adversary can always target specifically those paths to cut. On a side note though, different from deleted edges, edges that are newly created do not pose fundamental problems for the algorithms. Because of this, in this presentation, we will focus on mainly how to deal with deleted edges. Our paper explains how we handle newly created edges. So coming back, how do we address this fundamental problem? So to explain this, let's focus on how to propagate a value from just one node v to the root. Previously, when we use spanning tree, then v only has a single path on the tree to the root. If this path gets cut, then this value will get stuck. So our key idea here is to avoid pre-committing to any specific path for propagating the value. Instead, we use the set of all paths of length at most d from v to root. In general, this can be a huge set and may contain exponential number of paths. But this set has the following nice property. For every t consecutive rounds, the t-interval model guarantees that there is at least one path in this set that remains stable throughout all those t rounds and can never be cut. In short, this set contains at least one stable path. In our simple example here, d is 4. So we consider all paths of length at most 4. There are 4 such paths from node v to node root. Note that some of the paths actually need to go to the opposite direction first before going towards the root. Now, node v will look at the set and split its value of 1 into 4 equal pieces, 1 for each path. All these pieces will then propagate along their respective paths, all in parallel, and taking OD rounds. In our example, each piece corresponds to a value of 1 over 4, since there are 4 paths. Remember that every node in the network, and not just V, will need to do this. So every node will potentially need to deal with an exponential number of paths. How to do proper bookkeeping of this exponential number of paths will be a central challenge, and we will overcome this central challenge later. Now, with the previous idea of massively parallel aggregation, let's take a look at what happens now when some of the edges got cut. So in turn, this will cause some of the paths to get cut, which in turn causes some of the pieces to get stuck instead of arriving at the root. However, note that a piece can only get stuck when both of the following conditions hold simultaneously. First, the path was still available and not yet cut when the algorithm computes the available path. Second, the path must then get cut right when that path was being used. Putting it another way, the adversary has to cut this edge within a certain vulnerability window in order to cause the piece to get stuck. If the path got cut outside of this vulnerability window, then nothing bad will happen. So to repeat, a piece can only get stuck if the path was available when we computed the number of paths, but later some edge in the path got cut when the value is propagated. This leads to the following idea. We stagger the propagation and we spread our stakes. Specifically, we will divide the rounds into X sequential intervals, where each interval is OD rounds. Consider a node V. Each interval will only be responsible for propagating 1 over X fraction of this value to the root. Within each interval, we first compute the available paths and we propagate the values along those paths. Note that within each interval, we still need to do the propagation via all the paths. This means that the 1 over X fraction of the value will get split furthermore inside each interval into more smaller pieces. Now, for any given an edge, if the adversary cut that edge, the adversary now can only cause damage to just one interval, which is the interval containing the round where the edge is being cut. Furthermore, there is only so many edges that the adversary can eventually cut. This combined and some simple calculation, we can then show that by using about d log n intervals, we can ensure that at least half of the value from each node will get to the root. So to summarize what we have so far, at the end of all these d log n intervals, half of the values will reach the root node. But that means that half of the value may still get stuck, and they may be simply left in various locations across the network. Now, in order to collect these stuck values, we repeat the entire process again. When we do so, a node collecting A node holding some of the stuck values will be viewed as the nodes whose values need to be propagated to the root. This means that the starting value on some nodes may no longer be 1, and sometimes may even be more than 1. Also, notice that the stuck pieces do not aim to go back to their respective original nodes. Instead, their only goal is to reach the root. With such a design, after each such process, the root node will collect at least half of the remaining values in the network. By repeating this for a logarithmic number of times, the root will then be able to collect most of the values, which ultimately allows it to compute n. Up to this point, we have covered several of our key ideas. All these ideas together can roughly leads to an d square log square n time complexity for count. The caveat is that we have made a number of significant assumptions and skipped some critical difficulties along the way. Amongst those, one central difficulty is how to do bookkeeping for the exponential number of paths. Next, I will explain how we deal with this central difficulty. First, let's clarify what exactly this difficulty is. Consider the following example where d is 4. In this example, we have a value of 1 at node v and a value of 1 at node w that needs to be propagated to the root. Node v has 5 paths to the root of length at most d, so it will split its value into 5 pieces. Furthermore, amongst these paths, 3 of them has u as its second node, so 3 of these pieces will move to u. In a similar way, node W has 3 paths to the root of length at most d, so it will split its value into 3 pieces. 2 of these paths have u as its second node, and hence 2 of these pieces will go to u. So let's focus on the pieces on node u, and let's for now forget about the rest. So the problem here is that it is unclear what node u should do with all these pieces. It gets 3 pieces from node v and 2 pieces from node w. Each piece needs to follow their own respective paths, and u needs to somehow route these pieces to their respective next hops. So it seems that in order to do this, the pieces needs to have its path information on it. But with exponential number of paths and pieces, doing so is just prohibitively expensive. What can we do about it? Interestingly, we observe that allowing paths to contain repeated nodes helps to overcome these problems. To see why it helps, consider what happens if we allow repeated nodes in the earlier graph. Now, there are still 5 paths of length at most 4 from v to root, with 3 of them having node u as a second node. But for node w, there are now 8 paths from node w to root of length at most 4, and 3 of them has node u as a second node. I did not draw all these 8 paths in the graph, but you can verify them if you'd like. Now, notice that both v and w have the same number of paths with node u as its second node on the path. This is not a coincidence. In fact, the number of paths with u at the second node always equal the number of paths from u to root of length at most d minus 1. This simple property turns out to be critical in dealing with the bookkeeping problem we were having. Now, let's come back to the earlier example to see how things have changed if we allow paths to contain repeated nodes. At the top, we still have the old example where the paths do not contain repeated nodes. Now, if we allow the paths to contain repeated nodes, v and w will send 3 pieces to u. These pieces will still need to follow their own respective paths. But now, u will always receive the exact same number of pieces from both v and w. Furthermore, these pieces will always follow the same pair of paths. Thus, these pieces can now be grouped together and be sent together. In fact, all that node you need to do is it should forward one group pieces along each of the 3 paths from node u to root of length at most d minus 1. This effectively means that the pieces can now be processed in a memoryless way. There is no longer a need to attach path information on each piece. Now, in this example, node u needs to send exactly one group to each of the 3 nodes. But in general, a node can send different number of groups to different neighbors. Furthermore, in this example, node u sends total 3 messages. Our paper describes a simple additional technique using which we are able to propagate all the values to all its neighbors while just using one message. Now, while we have covered some of the key ideas in our paper, these ideas are still not sufficient to get our results. In our paper, we explain in more details what are the remaining non-trivial challenges left and how we deal with them. To conclude, our central contribution in this work is a novel framework for designing algorithms in T-interval dynamic networks when T is not too small. Our framework builds upon a complementary set of techniques, some of which we have covered during this presentation. By applying our framework to various fundamental problems, we obtain novel deterministic algorithms with only d cubed log square n time complexity for solving those problems. These algorithms are the very first such algorithms which do not have theta n term in its time complexity. This is the end of the presentation. Thank you for watching.